Okay, we're live now. All right, let's do number 4. So, right, there's our incline, there's our skier. It's beautiful. Always, 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 when you are dealing with an inclined plane, the first forces you should put on there, your F parallel going down the ramp and your F perpendicular going into the ramp. Those always exist, okay? Always exist. It doesn't matter the type of inclined plane question, those forces always, always, always exist, okay? We also have this normal force because we have contact between the ramp and the thing. If we didn't have contact, we'd be flying, okay? Cool. The only difference now is we've got some friction, right? Because this skier is going to accelerate down the ramp, which means the friction is going to go in the opposite direction here, which means we also need to say that down the ramp is going to be our positive direction because we are going to get a positive acceleration out at the end. So that's fantastic. So if we take this and we look at the net force equations, okay, we are going to get the sum of the forces in the parallel direction. Well, we're going to get F parallel minus the force of friction. And then we're going to get the sum of the forces in the perpendicular direction, which is Fn minus F perpendicular. Okay. Now, since we're dealing with friction, we need to use this to find, I can't spell, I can't write, to find Fn, right? We need to use that to find Fn for our friction. Cool. So we can say that we know that Fn minus F perpendicular is equal to 0 since the skier is not leaving the surface of the ramp. There's no acceleration in that direction, just like before. So our normal force is equal to F perpendicular, which is just equal to mg cos theta. Cool. Okay. Can we calculate that? We got the angle, we have gravity, but we are missing the mass, right? We are not given the mass. That's okay. We want it to cancel. Remember? So that's totally cool. We can leave it as is for now. Okay. Now let's go back to the x direction. I'm going to do it in blue, or sorry, in the parallel direction. Okay. We know that we're going to get F parallel minus the force of friction will equal mass times acceleration. F equals ma. We've been doing it this entire time. Hasn't changed. Okay. Where if we plug some stuff in now, we know what our F parallel is. That's mg sine theta. That never changes. F parallel is always mg sine theta. Okay. But our force of friction is mu Fn. Okay. Do we know what Fn is? We don't have a number for it, but we have a formula for it that we could definitely take and plug this right into our friction, which tells us that mg sine theta minus mu mg cos theta is equal to ma. So we just plugged in the normal force right there for mg cos theta. Okay. One small thing, don't forget the mu, right? That mu, don't forget it. A lot of students just get excited when they plug stuff in and they just forget to write the mu. That's important. It was part of the formula beforehand. That's part of your force of friction. So you need to keep it afterwards. And this right here is super beautiful because we've got a mass in every single term and that can cancel out, which means our acceleration is just going to be g sine theta minus mu g cos theta. We have all those values. It simplifies down very nicely. Same idea here. Try not to forget mu. Okay, mu gets left behind really, really easily, so just be careful about that. So this is fine. Let's plug our stuff in. 9.81 times the sine of 65 degrees minus 0. I don't remember what it was, 12. Where do you go? 0.12 times 9.81 times the cos of 65 degrees, which means we get a good old acceleration of 8.4 meters per second squared. Yay! Exactly the same question, but we just sprinkled some friction in there. It's great, okay? And now that we have our acceleration, if we want to know how fast they're going, we can now use our kinematics to find the final velocity, right? We want the final velocity. We know they are starting from rest. We just found our acceleration down the ramp, and we know they're going for 8 seconds. So this is just a super quick calculation. This is nothing fancy here. Our final velocity is just going to be 8.4 times 8 seconds, which means our final velocity is going to be a good old 67 meters per second. I mean, that is a pretty steep slope, 67 meters per second. That's really, really fast. That's extremely fast. That is what, 67 times 3.6. That's 240 kilometers an hour. I don't know anything about downhill skiing, about like professional downhill skiing. I know I can downhill ski, but I don't know. I don't think I've ever gone that fast in skis. I don't know how fast people go. Does anybody know? Like if you watch the Olympics, does anyone know how fast they zoom down those hills? Probably not that fast. Cool. And that is a beautiful inclined plane question. Yay! Let's go back up. Let's do question number 3. Okay, question number 3. A car can accelerate on level road from rest to 21 meters per second in 14 seconds. What is the steepest frictionless slope this car can climb? Now, this question's a little bit weird. It is, okay? What it's asking us, okay? We're at some theta, and we have this car that is trying to climb this road, okay? Now, there's a couple different ways of looking at this question, okay? When this car is climbing this road, you can think of it, okay, we know for sure that there's F parallel going down the ramp and there's F perpendicular going into the ramp. We've got our normal force and there's no friction, okay? But so this car is trying to apply a force and it's trying to push this car up the ramp, okay? But we don't know what that applied force is, right? We know F parallel and F perpendicular because that's just our components, mg sine and cos theta, but we don't know the applied force. But what we do know is that it can go from rest to 21 meters per second in 14 seconds, right? Which means that our final velocity equals VI plus AT, exactly the same formula. We're always bringing kinematics into this, which means our acceleration is just V final divided by T, which is 21 divided by 14, which means we get an acceleration of 1.5 meters per second. This acceleration is the max acceleration this car can handle. Okay, that's how much it can apply, which means the maximum force this car can apply, or the engine can apply, will just be an FA, the mass of the car, times this acceleration of the car. Okay, that's it. That's as fast as this car can go. That's as much force as it can go, which means if we look back at our free body diagram over here, we know the motion of the car is going up the ramp, which means we will get the sum of the forces in the parallel direction being FA minus F parallel, okay? But this is where things are gonna get a little weird. This FA, right? This thing, it's gonna equal mass times acceleration, but this car is not going to accelerate up the ramp, right? If the steepest thing, this car is trying everything it can do, but it can't climb this hill, right? So it's just stuck there, right? Here is my ramp, okay? Here is my car. This car can go on flat ground. It goes, okay? Increase a little bit, this car can still go, but it doesn't go as fast, okay? Increase it a little bit, it can still climb, but it does it slower. Eventually, you're gonna get to an angle where this thing is trying as much as possible, but it can't. This thing's going vroom, 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 but it can't do it. It's not sliding down the ramp, but it's also not climbing. It's just kind of stuck there, okay? That's what's happening here. We have a car applying the maximum force that it can, which is mass times acceleration, 1.5 meters per second squared, but it's not going anywhere, okay? Which means our F applied is just going to equal F parallel. Now remember, we're looking for the angle. We want to know how steep it gets, which means, I don't know why I put the arrow over there, right? Mass times acceleration is going to equal to mg sine theta. Our mass canceled out. I told you it's always going to happen, okay? Which means I need to give myself more room because I didn't plan this out well. There we go, okay? Which means that sine theta is going to be the acceleration divided by gravity. Take the sine inverse, A over G, which is going to be the sine inverse of 1.5 over 9.81. You plug that into your calculator. I need to give myself more room. You plug that into your calculator, dun, 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 dun. You should get an angle of 8.8 degrees. That is as steep of a car as an incline this car can climb based on how much power this car has. It's a little bit of a different question, a little bit different way of thinking about it, but it's looking at questions in a different way where the idea is, right, we can apply a force and not go anywhere. That's the whole magic of dynamics. You can have forces, but if that force is balanced out completely with either friction or in this case, just F parallel, that force pushing the thing down the ramp, then you don't get any motion, okay? This one, not gonna lie, I'm gonna say this is a harder question. The math isn't hard, not at all, but the concepts, thinking, setting it up is a little bit weird. Okay, cool. 2 questions down. I think we have 2 more maybe. We got a wagon, and then we got a race car. Okay, cool. 2 more questions. Here we go. So we've got a person dragging a 20-kilogram wagon up a 15-degree hill at a constant speed. Person's pulling with an 80 Newton force parallel to the incline. That's all great. We want to figure out what is the coefficient of friction between the wagon and the hill. Okay, so let's draw a picture, right? We always start with drawing a picture. So we've got our hill, like so, and we've got our wagon on the hill. Cool. Okay. Now, this thing is being pulled upwards, pulled up the hill, which means we probably want to make up as positive because we are moving up the hill. So if we're moving up the hill, we need to have some type of applied force that is going to get us up the hill. Okay. Now, if it's going up the hill, oh my goodness, where'd you go? If it's going up the hill, that means that the force of friction is going to go down the hill. Now, we forgot two very important things, three actually, but two very, very important things that always exist with inclined planes. We have our F parallel and our F perpendicular. Look at all these lines, it's beautiful. And of course, this person's not flying off the hill, so we still have our normal force. It's beautiful, it's absolutely beautiful. Okay, so since we are asking for the coefficient of friction, that means that we care about friction, which means, you know what, we probably need to find Fn. That's going to be important. The other thing in this question that's an important piece of information is that we're dragging this up the hill at a constant speed. A constant speed is a key word in these questions because that tells you that your acceleration is equal to 0. You are not changing your speed at all. Your acceleration is equal to 0. So let's just go ahead, let's jump into the sum of the forces. I'm going to start in the perpendicular direction because the more of these inclined plane questions you do, the more you realize that there is a pattern. I don't want to say always, but in this course, the normal force is always just going to be mg cos theta. Okay, it is. It's great. Okay, now if you notice something else about this question, we have a mass. We have a mass. Yay! Which means we can just plug stuff in, right? Since we have a mass, we can go ahead and plug in the 20 kilogram wagon times gravity times a cos of 15 degrees, which means we can get an actual value, a number, a beautiful number. I know how much y'all love numbers for our normal force. Our normal force is actually, I'll plug this in, 20 times 9.81 times the cos of 15 degrees, 189.5 newtons, okay? I'm gonna give it a little highlight, not the answer, but it's a good start. So now that we have, I'll do it in black again. Now that we have our normal force, we can go ahead, jump over to our parallel direction. And in this case, the sum of the forces in the parallel direction, we're going up the ramp. So we've got our F parallel. We are fighting against F parallel, and we are fighting against the force of friction. Okay. And this whole thing, I'm just going to save space and say it's equal to 0. And it is equal to 0 because constant speed right there, our acceleration is equal to 0. So that makes this formula much, much nicer. Okay. Now we look closer at this. We want the coefficient of friction, which means we are looking at this term. Okay. That's what we want because we know that term involves mu Fn and we already found Fn. So that is what we are looking for. Our applied force right there is beautiful. That's 80 newtons. It tells us that in the question, they're pulling with a force of 80 newtons. F parallel, that's great. We always know F parallel. So we can go ahead and say that the force of friction is just equal to FA minus F parallel. If we just punch some numbers in here, mu Fn, mu Fn, we've got 80 newtons. We are fighting against 20 times 9.81 times the sine of 15 degrees. There's our F parallel, okay? Which means mu is going to be whatever that number is. Let's figure it out. 8 minus 20 times 9.81 times the sine of 15 degrees. 29.2, all divided by our 189.5. So far, those numbers look, I'm happy with those numbers because we're going to get a very small decimal and we get 0.15, which makes sense. That is a reasonable value for coefficient of friction. So we are good. Cool. Yay. Look at it. Okay, super fun. This is about as complicated, this is as complicated as a question can get. 3 forces in the parallel direction: an applied force, a parallel force, and a force of friction. That's as complicated as it can get. When you are dealing with an applied force, you're most likely going to be given the mass because applied forces have nothing to do with masses. So you can't cancel out if you don't have the mass, right? If you have an applied force, okay? Now, after 10 minutes, person gets tired, lets go of the wagon. It's great. Starts to slide down. I want you to try this one, okay? I'm not going to put a video or anything to this. It's similar to part A, except now there's no more applied force, okay? So try this question. The answer is it slides 13 meters. So try that on your own. See if you can get it. I'll put out a nice solution onto the notes so you can go ahead and check your notes, but I'm not going to put a video for this question, okay? Because it's very similar to part A. Okay. Here we go. The last question. Last question. I love these types of questions, okay? A race car is moving at 25 meters per second when it encounters a 22-degree hill with a coefficient of friction of 0.18. At the bottom of the hill, the driver takes their foot off the gas and coasts up the hill. What distance up the incline can the race car travel? Now, what's happening with this question? Here we have our race car. Here we have our hill. This car is going vroom, 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 vroom. As soon as it reaches the bottom of the hill, this thing stops putting any effort in. It just says, okay. And eventually, it's going to slow down, slow down, slow down, and it's going to stop. And if they don't do anything, it's going to roll right back down, right? This car is not applying any force to climb the hill. It is strictly climbing the hill based on the momentum that it had, okay? So when we read this question and it says, takes their foot off the gas and coasts up the hill, that means that the applied force is equal to 0 newtons, okay? The car is doing nothing to climb the hill. Nothing at all, okay? So what this picture looks like, we get our incline and we get our race car, okay? We have our 2 forces that are always there, F parallel going down the ramp, F perpendicular going into the ramp, and our normal force going up. That's always the same, okay? Now, what we don't have is this, okay? There is no FA. This is bad. Don't do this, right? Bad, bad, bad. There's no FA up there, right? Because this car is not doing anything. This car says very clearly their foot is off the gas and they are coasting up the hill, okay? They are fighting against gravity, okay? So they're fighting against gravity. They're moving up the ramp like this, so we'll say that direction is positive, but they're also fighting against another force, the force of friction, because there is friction of 0.18, okay? So they're coasting up the hill with this initial speed. They're getting stuff taken away from them by friction and just the fact that they're climbing a hill, which means the acceleration that we get here, right? Our acceleration is going to be negative. And it's going to be negative because it's slowing down as it climbs the hill. Slowing down as it climbs, okay? Now, as it's approaching the hill, right, this thing is going up this way. We've got an initial velocity of 25 meters per second, going like that, and it's going to reach some point up here where its final velocity will be 0. It's going to have 25 meters, it's going to have some type of acceleration slowing it down, and then it's going to stop, okay? So let's go ahead, look at the kinematics here. I might as well keep doing this all in pink because why not? The sum of the forces, I'm going to start with the perpendicular direction just because. Do you see the pattern yet? Fn minus F perpendicular. Fn is equal to F perpendicular. Fn mg cos theta. Can't plug it in this time, don't have a mass, which means it's going to cancel. Yay! Cool. So that's step 1. There we go. Move it up here a little bit. There we go. Next part, F parallel, sorry. We only have 2 forces. We have negative, the force of friction, and negative F parallel. Both are going down the ramp. Since we defined, right, maybe I should turn this pink too. We said up the ramp was positive. Both these forces are going down the ramp, which means both of them are negative, okay? Which means negative the force of friction, negative F parallel is going to equal mass times acceleration. All of those negatives make me happy because it looks like we are going to get a negative acceleration, okay? Let's plug some stuff in here. We know what this formula is made of. Negative mu mg cos theta, that's our force of friction right there, minus mg sine theta, there's our F parallel, that equals mass times acceleration. Oh my goodness, just like we expected. Goodbye mass, it's gone. And that leaves us, I'm just going to write the A on this side, negative mu g cos theta minus g sine theta. This looks exactly like the question we did before. Inclined planes, the math always works out pretty much exactly the same, not going to lie. So if we just punch our values in, negative 0.18 times 9.81 times the cos 22 degrees minus 9.81 times the sine of 22 degrees, just like so. We should get an acceleration of negative 5.3 meters per second squared. Give it a little highlight. We're not done. That's not the answer because the answer is the distance. Okay. Now this is just a strictly a kinematics question. That's it. So what's happening here, right? Now that we can go to kinematics, I'll do it in purple. We have this car coming in like this with an initial velocity of 25 meters per second. And then it's climbing a hill like this. The hill itself is 22 degrees, okay? It's slowing down with an acceleration of negative 5.3 meters per second squared, stopping some distance, I will call this delta x, up the ramp, That's what we're looking for, okay? Which means that's a relatively straightforward kinematics question. We don't care at all about time. We know stuff about our initial and final speeds, plus 2a, I'll call that delta x. That's our beautiful formula. We're going to rest. You can solve that. I'm not going to go through all that kinematics, but you should get a delta x of 58.9 meters. Cool. And there is our answer. Now, because physics is amazing like this, there is another way to do this type of question, okay? We can look at it slightly different because you know what? What if you did everything that we just did here? All of this good stuff, okay? Goody, goody, good stuff. That's all pink. What if we went back to our picture and instead, I will do it in green. What if we said down the ramp was positive? It would work, right? But now, since our initial velocity is going up the ramp, and we're moving, and we said down the ramp is positive, your initial velocity is actually negative 25. And your acceleration should be positive. Exact same question, but now the negatives and positives are going to flip. The sum of the forces for this one, right? If we look at the parallel direction, is now going to be the force of friction plus F parallel. Instead of adding them up to be negative like we did over here, you add them up to be positive, you get a positive acceleration, but you start with a negative velocity. Or start with a positive velocity, get a negative acceleration over here, and then figure out the slowing down. Don't care how you do it. Both are exactly the same. Both are totally cool and will get you exactly the same answer. Congratulations. We are done dynamics. We know everything there is about dynamics and we know everything we need to know about inclined planes. Awesome. Love it. So I'm going to stop